In this video, I will be starting this unit on word problems. They're word problems involving linear equations or inequalities. Okay, I know a lot of people struggle or get intimidated when they are given a word problem, mainly how do they even begin? They're given a bunch of words, how do they pick out the pieces, write it in terms of equations or expressions or whatever it may be. Okay, so hopefully as you go through this series and as you practice more problems, you get the techniques down. You read the problem, you pick out the key words and key numbers. Maybe there's some information that's a distraction and actually irrelevant to the problem. So you need to be able to figure that out. So of course, I'll give you some general strategies, but as with most skills, you got to practice it in order to get better at it. All right. So let's begin. So this is from an SAT prep book, and this is just describing the general strategy to go about to solve word problems for the SAT. Okay, so let me even get out the laser pointer. Okay, so it says to find out what numbers are asked. Okay, so for example, if usually it's like in the last sentence or two, they'll ask you like, oh, find the distance, or find the amount of time taken to do this, or find the amounts that is needed for this scenario, something like that. So just identify what they're asking for. If there's some unknown, like that thing that we're trying to find, choose some variable to represent it. You can just call it X. That's totally fine. If there's more than one unknown in the problem, it might be a little smarter to just, instead of just naming variables X, Y, Z, I mean, that's totally fine. If you're comfortable with that, by all means, go ahead and do it. If it's like time that you're trying to find, maybe represent it as T. If like they give you the speed of something, maybe represent it as S. So whatever helps you. It doesn't have to always be X, Y or something like that. You can choose A, or you can choose theta, alpha, you can choose any other, it doesn't matter. Okay? Find an equation that represents relationships among the numbers in the problem. So in this unit, it will be linear, so it'll be something like y equals mx plus b. Okay, and I'll go over that in the next slide. So after you write the equation, solve the equation for the unknown. Okay, and then answer the original question, check your answer is reasonable. So the key thing for number 5 is sometimes you're busy finding something that's needed to answer the original question, but that's not exactly what the question was asking for. So for example, in one of the upcoming problems, it asked like, oh, this person started with maybe 10 gallons of something, and then how much is left after 2 hours? So you might find out that, oh, in those 2 hours, maybe 2 gallons were used up. So you should be answering the question with 10 minus 2, which is 8. 8 gallons is left. Don't just report that the answer is true. That's not what the question is asking for. She used 2 gallons, not there isn't 2 gallons left, there's 8 gallons left, 10 minus 2, something like that. So it'll be clear when I go through some of the examples. Okay, so this is a repeat of the last point, but a linear function can be used as a model for scenarios with a constant rate of change. That's the key phrase, a constant rate of change. Rate of change does not change. So in many scenarios, time is the independent variable. So maybe instead of x, write as t, y equals mt plus b. That's kind of weird, but it's more intuitive sometimes if you write it in variables that kind of match what it represents. Instead of x, write as t for time. Okay, so what does this model actually say? So if we ignore the plus b first, the model is basically saying quantity equals rate times time. So y is the quantity, the final quantity, m is the rate, t is the amount of time. Okay, so if we use a very simple example that you probably know, distance equals rate times time, with speed times time. This is a very specific application of this more general case, quantity equals rate times time. Okay, the quantity is distance, the rate is the speed, and then time's the same. That's the independent variable. Okay, so if we use some actual numbers to further illustrate the point, if like the speed of a car is 60 miles per hour, and the car is driven for like 2 hours, then intuitively you would think, oh, it went 120 miles per hour. Why did it go 120 miles per hour? You did 60 times 2 in your head. And that is the rate times time. And this gives you the quantity right there. All right, so that's just a very specific application. Now, sometimes the units actually help a lot. I know for some students, they don't like working with the units, but as you do more problems and you actually write the units out, you can see that it can help greatly. It really helps to see if you did the math correctly. If they're asking for the time and the units that you got were in miles, then clearly you did not do something right. Okay, so write out the units. For example, here, in this multiplication here, miles per hour times hour, the hours would cancel and you get miles. So that's why it worked well. At least we got the right units. Maybe we did, even if you did some math wrong, at least, at the very least, you had the units right. Okay, and to finish off, we were ignoring this plus b. What this plus b really is the initial value of the quantity. So you think about it. When t is 0, no time has passed, you plug in t is 0, you get y equals 0 plus b, so y equals b. That's the initial quantity. Okay, so now let's go through some problems. Number 1. At the beginning of a trip, the tank of Chloe's car was filled with 12 gallons of gas. When she travels constantly on the highway 60 miles per hour, their car consumes 1 gallon of gas per 35 miles. If she traveled 5 hours and 15 minutes on the highway with a constant speed of 60 miles per hour, how many gallons of gas are left in the tank? So I'll give you a minute to try this yourself. Of course, I'm not actually going to wait a minute, so please pause the video if you want to try this yourself first. And then unpause it to see how I thought through the problem. Okay, hopefully you tried it. So there's lots of words. So the first challenge is to pick out the key points, okay? So the question is usually at the end. So it's asking how many gallons of gas are left in the tank. So if you remember the model, quantity is rate times time. It's asking for quantity, gallons, okay? So we would need a rate and a time in order to find it using that linear model, okay? So again, use the units to help you out. Problem provides 2 different rates. There's one for the speed of the car, 60 miles per hour. Okay, that's right there. And the gas mileage is another rate, 30 miles per gallon. Okay. Now, they did give us a time, because we also need that, because remember, quantity is rate times time. We've identified the 2 rates. We might need both of them, and we'll use the units to help us out later. Okay. The time is 5 hours and 15 minutes. You probably want to make this all in terms of minutes or all in terms of hours. Probably all in terms of hours because the speed is in terms of hours, miles per hour. So you probably want to make it in hours. So 15 minutes is a fourth of an hour. So 5 hours and 15 minutes is 5.25 hours. We have a common unit now. Okay, so as I was saying, let's use the units to help us out. 60 miles per hour. So 60 miles per 1 hour. If we multiply it by 1 gallon every 35 miles, so 1 gallon per 35 miles, the miles would cancel, so we get gallons per hour. So now let's multiply it by 5.25 hours. So this was the rate, this is the time, okay? So now the hours would cancel, and you're left with just gallons as the unit, okay? And 60 divided by 35 times 5.25, just plug into a calculator, should be allowed in most of these problems. It's 9 gallons, okay? So here, exactly as I was saying, we got to answer the question. This is multiple choice. It doesn't have a choice of 9, so we're safe there. But what if they put like choice E, 9? Don't be tempted to circle that. This doesn't answer the question. She used 9 gallons in this drive. So how many gallons are left? She filled it with 12. So it's 12 minus 9, which is 3 gallons left. So the answer is A. Okay. Number 2. A rock climber is climbing up a 450 feet high cliff. By 9:30 a.m., the climber reached 90 feet up the cliff, and by 11 a.m., he has reached 210 feet up the cliff. If he climbs with a constant speed, by what time will he reach the top of the cliff? So go ahead and pause the video to try solving this yourself first. Okay. So, as always, what did they ask for? They're asking for time. So in the quantity equals rate times time, we need a quantity and a rate. So what's the rate? So in units, by the way, it should be feet per hour. So that should help you out right there also. they give us two different time points. 9:30 a.m. he was at 90 feet. 11 a.m. he was at 210 feet. So we can, because it's a constant speed or a constant rate, we can just find the slope, okay, or the difference between the distance divided by the time. Distance meaning height in this case. So delta height over delta time, or change in height over change in time, that's the slope. If this were like a linear line, if we drew it as a line, it would be the slope. So what is that? That's 210 minus 90 over, by the way, from 9:30 to 11, that's 1.5 hours. So 1.5 hours is down there, which is 80 feet per hour. So this is the rate. Okay, now what about the quantity? Okay, so how much distance is left to the top after, once it's 11 a.m.? So the mountain, or not mountain, the cliff is 450 feet. He went up 210 feet already. So how much is left? That is 240 feet. Okay, so now we use that model once again. Quantity equals rate times time. So the time is quantity over rate. Okay, so at 80 feet per hour, that's the rate. Climber needs, so quantity 240 divided by rate, and you can see the feet, units of feet would cancel. The hour is at the bottom here, so you can move up to top. So it's 3 hours. So he needs 3 hours more to get to the top. So 3 hours after 11 a.m. is 2 p.m. The answer is B. Okay. Hopefully you're getting more of the hang of it now. Next. In 2005, a house was purchased for $280,000, and in 2013, it was sold at $334,000. Assuming that the value of the house increased at a constant annual rate, that's key. What will the price of the house in the year? What will be the price of the house in the year 2018? Okay, so go ahead and pause the video to try this yourself. Okay, so clearly this is the old book that I pulled this from because it's asking about the price in 2018 as of the filming of this video. It's 2024, right? By the way, so what did they ask for? They asked for quantity this time. They're asking for the price. That's the quantity. It's not a time, right? And it's not a rate. So it's quantity. So we need a rate and a time as a result. Okay. So how much was the cost of the house increasing per year? That's the rate. So we're going to use the 2 points given again, like in the previous problem. So 334,000 minus 280,000 over 2013 minus 2005. The units will be dollar per year, or dollars per year. So this is $6,750 per year. This is how much it increased, $6,750 per year. Okay, so 2018 is 5 more years after 2013. Okay, therefore, the price will increase by, this is the rates that we just found. The time is 5 years. So the years would cancel, you're left with dollars, and it is $33,750. Okay, now again, be careful to answer the question. This is how much it increases from 2013 to 2018. We got to add this value to the value it already was at 2013. So we got to add to the 334,000. That's what I did here. 334,000 plus 33,750 is equal to this number. So the answer is C. So I'm actually quite surprised that I didn't put a choice where it was, you just add one more zero here. 337,500. Because I feel like some people, once they get here, will start looking for an answer. They'd be like, oh, this one's the closest. I probably just made some small error and then circle that one. So they didn't answer the question if that was the case. All right, next. To join East Lake Country Club, one must pay D dollars for a one-time membership fee and pay W dollars for a monthly fee. If the first month is free for the club, what is the total amount Y X months after a person joined the club in terms of D, W, and X? Okay, I hope you paused the video to solve this yourself first. So we're going to go step by step, adding one or subtracting one thing at a time. Okay, so it says that there is So I guess over here, I didn't go through all this, but there's a one-time membership fee. So remember in that lesson slide, I was saying there's an initial value when t is 0, the b is the initial value, and the y equals mt plus b model. This is the initial value d over here. All right. Now, there's a monthly fee of W dollars. So every month that you stay there, it's W more dollars. So you can imagine it's like WX, W times X, W dollars times X number of months, because it's W dollars per month. I didn't write the units here, but W dollars over month, that's the unit. So times X months, so the month would cancel and you're left with dollars. So WX dollars. Okay, so that's what I did here, WX. Add the one-time fee that we said was that B in the linear model, so WX plus D. Now they changed things up here a little bit. The first month is free. So we would have to subtract a W from here. So that's what I did here. So I'm just going slowly here to show my work. The WX plus D minus W for the first month being free. So we can move this to here. Okay, and then you factor out the W. So it's W times X minus 1 plus D. This also makes sense if you were able to jump to here immediately. Great. Why does this make sense? Well, because the first month is free, if you join for X months, whoops, then you just pay X minus 1 months. That's why it's like this. Okay, so that's the answer. And as a result, we can eliminate C, D, and it looks like it is B. Okay, I believe there's two more. The free response now. From 1990 to 2000, the population of City A rose from 12,000 to 28,000, and the population of City B rose from 18,000 to 24,000. If the population of the two cities increased at a constant rate, in what year was the population of both cities the same? So go ahead and try this yourself first. Okay, so here we will probably need to write two equations, one for City A and another for City B. Okay, so we're going to make two linear equations. And we're going to let x equal 0. So here I'm using x instead of that t model. So again, this is the variable. It doesn't matter what you call it. But I let x equal 0 correspond to 1990. So year 0, in a sense, is 1990. Okay, so for City A, since the rate of change is 28,000 minus 12,000 over 10 minus 0, which is 16,000, I just took the 2 points here. 28,000 minus 12,000, and elapsed was 10 years, right? So 10 minus 0. Remember, x is 0, x equals 0 corresponds to 1990. So 2,000 would correspond to x is 10. Okay, so this is like the slope. So the equation is 16,000x plus 12,000. So we can quickly check. When we plug in x is 0, remember that's 1990, we get y is 12,000, and that matches. We can plug in x is 10, we will get 12,000 plus 16,000, that is 28,000. Good. Okay. So we wait for B, we find the slope just as before. You will get 600. So the equation is 600x plus 18,000. Okay. Y, remember, represents the population. We want to know when the population was the same. The same. Yeah, I'm like, where's the same? Right here. That's where my mouse is. The same. Y is the population. So let's set them equal to each other. 1600, sorry. So 1,600 plus 1,600x plus 12,000, that's from City A's equation, equals 600x plus 18,000. That's City B's equation. So once again, y is the population. We're interested when the population is equal to each other. So we set the y's, the populations, equal to each other. That's what I did here. And we solve for x. So I moved all the x terms with x on one side to terms without x on the other side. So 10,000x is 6,000, which means x equals 6, which means they had the same population 6 years after 1990, or that means 1996. Again, the answer is not 6. They're asking for what year was the population the same. So it'll be 1990 plus 6, which equals 1996. And you can imagine that in year 6, actual year 6, it's going to be a negative number actually. So it doesn't even make sense at all. Well, I believe it's a negative number. It's going to not make sense if you just say it was year 6. Okay, so here, I believe this is the last one for this section. An empty 1,200 gallon tank is filled with water at a rate of 6 gallons of water per minute. At the same time, another 1,200 gallon tank full of water is being drained at a rate of 9 gallons per minute. How many minutes will it take for the same amount of water? How many minutes will it take for the same amount of water in both tanks to become the same? Did I read it right? How many minutes will it take for the amount of water in both tanks to become the same? Okay, there we go. That doesn't sound right as I read it out. Okay, so go ahead once again and try this problem. All right, so might be a good idea to set up 2 equations again. One for the one that started empty and the other one that started full. So tank 1 is the one that started empty. It's being filled at a rate of 6 gallons per minute. So y equals 6x. And the initial value, that b, remember, is 0 because it's empty. Versus here, in tank 2, I set it up as y equals 1,200 minus 9x. Why is that? Well, it's being drained, so that means the slope is negative because the amount is decreasing, okay? So that's why I put minus 9x, okay? And it started with 1,200 gallons, okay? So that's minus 9x plus 1,200, or 1,200 minus 9x, same thing. I just flipped the 2 terms around. Okay, and it makes sense because again, if you plug in x is 0, meaning nothing started yet, time is 0, y is 1,200. So that's the initial value. And same thing for tank 1, y would be 0. It's empty. That makes sense. Okay, so you want the time that it takes for the amount of water to be the same. So you want to get x when y is the same for both. So again, you set the y's equal to each other. So 6x is 1,200 minus 9x. That's what I wrote over here. And then you solve for x the time, exactly. So it'll be 15x is 1,200. X, if you do the math, it would be 80. So after 80 minutes, they will have the same amount of water. Okay, so hopefully this was helpful for you, just seeing how I thought through the problems, how I set up the problems, how I picked out the pieces, how I maybe even used the units to help me get the right answer. Okay, this is just part 1 of this series, or this chapter of the book technically. In the next video, I'll be doing more, and it will be more about like profits and more distance problems. So please look out for that video if you're interested. And hopefully I see you in that video. And please like and subscribe if you haven't already also.